so this works. All right. So first of all, I'm going to talk about some modelling work. Much of this work has been done by my PhD student, Rob Lloyd, who's skulking up the back there. And I'd very much encourage you to chat to him. He's got a poster outside where he's got a bit more technical detail about the models than I'm really going to cover today. And also my long-standing colleague, David Fletcher, who, as always, keeps our CFD models up to his high standards. I guess at this stage I might just skip quickly through these. We all know what Chiari malformation is. We all know that in a proportion of Chiari malformation patients, they also subsequently develop a syrinx, and that is associated with descent of the cerebellar tonsils into the upper cervical spinal canal. And those syrinxes typically form here below the level of the obstruction up here. As everybody's sort of said already this morning, and one of the nice things about speaking after everybody else is that you've heard all of this, so I have a little bit more time to talk about our work. The mechanisms driving the formation and enlargement of a syrinx are unclear, and we really don't understand the link between the obstructions to flow in the CSF, in this case up here, and how that drives fluid into the spinal cord to actually encourage formation of a syrinx. We do know, as Marcus also showed earlier, and I believe these are actually his images originally as well, if we intervene surgically to restore this CSF flow, then typically the syrinx will actually resolve. So clearly there's a causal relationship between obstruction to CSF flow and build-up of fluid in the spinal cord. We also know there's a lot of theories about the mechanisms. A lot of the early theories are based on the macroscopic hydrodynamics of the CSF. And Marcus has walked you through a number of these. And again, this is data from a study that we did a couple of years ago where we looked at tonsillar pulsation. So one of those leading theories is that the cerebellar tonsils basically act like a piston and create high pressure waves in the subarachnoid space. And what that suggested to some people was that was the pressure that was elevating pressure in the spinal subarachnoid space and thus encouraging fluid flow into the cord. Our study didn't really support that because we didn't find any differences in the cerebellar tonsil pulsations in Chiari patients who did have a syrinx compared to Chiari patients who did not have a syrinx. Of course, there might be other factors such as compliance of the spinal canal that would also play into this, but this method doesn't actually help us directly deal with that. So we have actually shown from some of our previous studies that there are differences in flow in CSF in Chiari malformation patients compared to controls. And we believe that one potential mechanism is what we call the leaky valve hypothesis. So we think that the differences in flow in the spinal subarachnoid space, and in particular some of that work has shown that there are differences in timing of the CSF flow in the subarachnoid space. And our hypothesis is this, so Marcus showed a different version of this sort of figure. And the idea basically is that at the time that the arterial pulse wave comes through these small penetrating arteries, arterioles, into the spinal cord, depending on the timing of this pulse wave, where this artery expands as the bolus of systolic blood flows through that artery, depending on that timing relative to the peak pressure or the CSF pressures in the spinal subarachnoid space, that this might act as a variable resistance valve. So that if the peak pressure arrives in the subarachnoid space at a time when say during diastole, where the perivascular spaces here are relatively large because the diameter of the arteriole is small, that would enhance inflow. And if that peak pressure arrived at a time at the same time as the peak arterial pulse wave in the penetrating artery, that would actually provide much more resistance to inflow. And similarly for outflow. So if the negative pressure in the subarachnoid space occurs at this point in time in the cardiac cycle, that would restrict outflow. Whereas if the negative pressure in the subarachnoid space associated with flow occurs when in diastole, that would actually enhance outflow. So We've previously used a simple model of this periarterial perivascular spaces, where we've modelled this simply as an annulus with a moving wall, simulating the expansion of the artery with the arterial pulse wave. And then we've applied the pressures at the subarachnoid space end of this model that were calculated from the real CSF flow from patients. So what we've shown from this model is that it is theoretically possible to, depending on the temporal offsets between the cardiac and the subarachnoid space pressure, to have a net inflow into the spinal cord. And in fact, just recently we've shown, if you look at the shape of the pressure profile in the subarachnoid space that drives that, it depends, you get enhanced inflow into the cord if you have longer periods of high CSF pressure, and they occur at particular times in the cardiac cycle when the perivascular space is widest. So the research questions that remain at this point for us were, we had this hypothesis with some sort of theoretical basis that at least shows us that that it's feasible, that there's some potential for this mechanism. But what we don't have at this point is hard experimental data to prove this theory. So that left us with these questions. One is, what's the real temporal offset between the cerebrospinal fluid pressure pulses in Chiari patients, and how does that compare to healthy controls, and how does that timing differ between patients with and without syrinxes? And the second question was, if we took a larger group of Chiari patients, how would those different temporal offsets that we measure experimentally actually predict fluid flow into the cord with this simplified model? And that's what I'm going to briefly talk about today. So what we've done in this study, the study that I'm going to show you, is we have done patient-specific models of a cohort of 24 subjects. Of that, we have a series of healthy controls, 9 healthy controls, and then the remaining subjects are Chiari patients with and without a syrinx. And we wanted to know, amongst those patients, what temporal offsets between the cardiac pulse and the CSF pulse would give us this enhanced inflow into the cord. And then we're going to compare those to estimated temporal offsets from the experimental data. So this was a reanalysis of an existing MRI study that was done by Liz Clark, and she was working as a postdoc with me a few years ago. And in this we had 8 Chiari patients without a syrinx, 7 with a syrinx, and 9 age and sex-matched healthy controls. We did phase contrast, cardiac-gated phase contrast MRI at the base of the skull, C2 and C5. The flow was analysed using 7, and this is the typical data that we got out. And you can see here that there are a similar overall profile in terms of the flow, but there are differences in the timing of that flow between the different groups. What we've done is to actually individually model each patient with their own input flow and their own anatomical geometry from that. One of the problems we had, if we then wanted to try and look at the cardiac timing, is that original study didn't actually aim to measure cardiac blood flow. And so what we've done is gone back and done a sort of a reanalysis where we've looked at the vertebral arteries here and manually tried to unphase wrap the problems that we had, because the velocities in the blood flow velocities are much higher than the encoding velocity that we used for the CSF. So it is possible to manually unwrap that. It's not an ideal method, but basically what that allowed us to do is to take a flow profile that looks like this, where these jumps here are caused by phase wraps from the encoding velocity being too low, and create a smooth profile from which we estimated the timing of the cardiac pulse relative to the CSF pulse. So the models basically look a little bit like this, and again, Rob's got some more information about these models in his poster outside, and I'm sure he'd be happy to walk you through them, where we've created subarachnoid space CFD models for each individual based on their MRI. in which the spinal cord and the outer part of the canal are considered rigid. We didn't include fluid structure interaction in these models because we previously showed that although the cord does move, it doesn't make a great deal of difference to the actual pressures. It just changes the local velocity distributions. We validated these models against measured CSF velocities at C2 and C5, and we used all individual patient-specific information for each person in each model. We then fed the pressures from those models at C2, so we took the output pressures at C2 and we fed those into our model of the perivascular space here, and assumed that the pressure in the subarachnoid space was driving this flow, and we looked again at a range of time offsets between the cardiac-driven expansion of the penetrating artery here, which narrows the perivascular space, and pressure timing. So what we saw from this was that I thought there was an image on the right-hand side there. No? It's sort of stuck halfway through drawing this. I'm not sure what's going on here, sorry. Problem with the thing. What we did see... Sorry, the figures aren't showing up. So what we did see from that analysis is in the larger cohort of patients, we did see that the negative peak pressures occur earlier in the Chiari patients without a syrinx and the controls. So there are differences in the timing of the pressure in the group, but similar to what Marcus noted earlier, is that in this group of people, the pressures of the Chiari patients who did not have a syrinx were actually different to the controls and the Chiari patients with a syrinx. And there were some other subtle differences in timing. So I'm sorry that the results are not showing up. There were very nice graphs there that showed you those things. When we put those pressures into the perivascular flow model, we similarly observed that there were significant differences in the predicted inflow, and that the temporal offsets for which there was enhanced flow into the cord actually was of the range of 4 to 15%, and the measured time offsets in the human data based on the unphased wrapped blood flow data was about 4.7 to 5.1%. So it's actually in the range of time offsets that would be expected according to this simplified model to actually cause increased flow into the spinal cord. So what that has suggested to us is that this leaky valve hypothesis is feasible. Again, it's not direct proof. It's very difficult to make direct measurements of CSF flow or fluid flow into the spinal cord, at least in humans. It's conceivable that this could be done in animals using contrast injections into the spinal canal, but we haven't done that yet. But these estimated phase differences could actually be promoting periarterial fluid transport into the spinal cord. I guess one sort of disclaimer is that the way we've done the timing analysis for the cardiac blood flow in the vertebral artery is obviously less than ideal because the original data was not collected with the correct phase encoding velocity. And so the timing data there needs improvement. So I'm just going to spend a minute now talking about where we're going from this. And one of the things that we've seen out of this data is that there are differences in the timing of CSF flow in the spinal subarachnoid space in Chiari patients, and there are differences between the patients who have a syrinx and do not have a syrinx. It's not clear at this point what the causes of that are and why is it that there are these differences in timing. And Rob's got some ideas on that, some interesting early observations from further analysis of some of this data, and I won't steal his glory, so I'd encourage you to go and speak to him. He's got some observations on his poster outside. But it's also made us, this study was retrospective, and we would quite like to do this properly in a prospective study where we can correctly analyse the blood flow and the CSF using the best quality methods, and that's a study that we have now ongoing. The other thing which a number of people have talked about today, and I think we're going to hear more about, is looking at the respiratory effects. And we've actually got a imaging study ongoing at the moment, where we're looking at the effect of breathing, so deep breathing and Valsalva manoeuvres on CSF flow in the spinal cord. And Rob's going to be doing models very similar to the sort of things that I've shown you today, based on the CSF flows measured from the respiratory effects. We'd also like to try and see if we can make our perivascular space model a little bit more realistic. And Marcus showed you some early data from ultrastructural studies that he's doing in his lab to try and better define the actual structure of the perivascular spaces, so that we can try and improve that model and make it a bit more realistic. And just to give you a flavour, how you asked me whether you can do time slip MRI in the cervical spine, or at least in the spine, and the answer is yes. So this is some example data. This is actually from a control. In this imaging study that we have running at the moment, we're using time slip, and you can see here that we tag a band of fluid, and then we can watch it. So this one's in a breath hold. At end expiration, you're seeing cardiac-only effects here. Here we have a combination of cardiac plus inspiratory inspiration, and you can see that the little bolus of fluid, there we go, actually moves further with inspiration. And this is a Valsalva manoeuvre where you can see we actually get quite different effects. So we're not quite sure what to make of this one yet. We're also doing real-time phase contrast, and also some other real-time imaging to look at tonsillar pulsations with respiration as part of that study. So just a teaser.
That's so exciting.
We like it. And again, just before I finish, I'd really like to particularly acknowledge Rob, who's really done all of the modelling work that I've presented today. Don't you love having great PhD students who make you look good? And David Fletcher, who keeps us both on the straight and narrow and makes sure our models are really technically beautiful. And also to Marcus and Liz for their previous work in a lot of this, and a lot of clinical input and discussions with Marcus in particular over many years, and our funders. Thank you.
I've been wondering, so for regular cysts in the body, not syringomyelia, how do they expand? And why, in syringomyelia, why wouldn't we assume it's similar?
So I'm not an expert on cysts in other parts of the body, but my understanding, very limited understanding, is that a lot of the time you get fluid drawn into a cyst because there's stuff in there, so it's a sort of an osmotic pressure situation. From what I understand, that there's not actually a big osmotic difference between fluid in a cyst and fluid in the spinal canal. And so we believe that that's not likely to be a major effect. I don't know, Marcus, you might want to comment more on that.
So there's not, well, just on the latter part, we've analysed the fluid from syrinx fluid versus subarachnoid space fluid in some patients. It's technically difficult to do this. We've not really found any difference. So it's essentially the same as CSF, so it's not osmotic. To answer your question, though, about cysts in other parts of the body, it's often a secretory cyst or a high protein cyst. I think it's really quite different. I don't think we're thinking here that there's a secretion, active secretion of fluid as part of the pathophysiology.
The source of the spinal fluid is parenchyma. At least 40% of CSF is created by the brain and spinal cord. A very small part is the spinal cord. That's why a syrinx takes so long to develop, is because it's only the parenchymal creation of extracellular fluid that flows into the central canal or wherever it's going that makes the CSF. Arachnoid cysts, for instance, also have a failed pia between them and the cyst. And they're also created by the development of CSF as a byproduct of brain or spinal cord metabolism. So it's just CSF. It's just like CSF that comes. in ventricle, there are two different kinds of CSF. One is choroidal, which is pure, and one is the parenchymal, which is less. They have a little bit of a different chemical balance. So this is like if you've done a choroid plexectomy, they'll still produce CSF and they'll still need their treatment, their hydrocephalus treated. So it's not only from the choroid plexus, but the spinal cord probably makes a cc and a half of spinal fluid a day, as opposed to the 200 cc's that are made a day by the brain, or in the choroid plexus and brain. But so that's the answer. I don't know about ovarian cysts or those sorts of things, but in the central nervous system, it's CSF that's been created and can't get out of whatever it's in.
So we know in the spinal cord that, so the tracer experiments that have been done, we know that actually quite a lot of fluid gets into the cord, into the central canal, and into a syrinx cavity in the post-traumatic models that comes from the spinal subarachnoid space. So it's not only fluid that's being created in the cord that's creating a syrinx.
Yeah.
So I think, I think of it fairly simplistically that you've got a cavity where you have an inflow and you have an outflow, and it gets bigger if the inflow exceeds the outflow. I think Marcus alluded to this morning, but there's been a lot of effort put into thinking about how fluid is getting in, including the modelling that I've just presented. And I think looking at where the fluid is going and how it's getting out, it's experimentally much more difficult to do, but it's a really, I think, challenging problem, and it's something that we need to start thinking about. I think there was somebody else who had a question over there. Yeah.
Well, last time in Amiens, I asked you about your theory about development of the silicon PLA, but everybody here in the room, I think, we know that there is some kind of pressure gradient along the spinal subarachnoid space. Many authors agree that pressure in neck is about 0, and the normal in lumbar space depends on how you long is subarachnoid space. It's pressure about maybe 50, 60, 70 centimeters of force. So we have many cases of the silicon area along 15 centimeters more. So, do you think that fluid from subarachnoid space go in syringe on the lower part, because we are 2/3 of our lifetime in head-up position and the pressure is higher in the lower part, and go in and up to the region where pressure is lower than normal.
Okay, so you bring up one point that I didn't make, which is that all of these models, the imaging is all done supine, and the validation of the models is all done supine. I think somebody else earlier asked about gravity, and the answer is we have not actually incorporated that in these models. And we are just, essentially we are simulating the supine condition. So I think it would be important to add that.
When are you going to do that, my dear? When can we hear from those results, please? Especially Valsalva in the erect position, if you've got a foramen magnum obstruction. Please come back and show it to us.
I'll try my best.
I think it's possible.
It is possible. It just
I
has,
don't know how you're going to do it, but I think
it's possible.
You've got the ability.
Well, we need to put the MRI machines.
Yeah, but then you've got the different artifact, haven't you, of somebody who's sitting up front, so...
Right,
I would
MRI.
like to be
So part of the problem is if you want to have a model that's validated, that actually corresponds to experimental data, you need a way of estimating the change in the flow associated with vertical position. So there's a very limited amount of inclination that you can do to a person lying in an MRI scanner. You can do a bit, and we haven't done that. But I guess my approach for a lot of these models is that I like to have validated models. I like to know that we're in the right ballpark and we've got flow velocities and things that are actually realistic, so that at least we're not completely out of the ballpark. But I think it's a good point, and I think that we could certainly simulate those effects. The problem is that we wouldn't know if what we were simulating was accurate because we haven't got measurements to compare it against.
Yeah, we did some experiments when we were looking at the spinal CSF, where you can prop the head up quite a bit in a normal bore magnet, and and you can get some some effect of gravitational variation. And if you're imaging the head, of course you can't. The cervical spine you can't. But
Further down,
with a
yeah.
spine coil,
Yeah.
you might try it.
Well, we can certainly try.